15.2 from AS Maths integration chapter, we're looking at finding functions. So when we integrate, we find what is known as a family of curves. Okay, and the thing that makes it a family of curves is this plus c on the end. So if we think about what effect that has, and it might make more sense to you to go back to y equals mx plus c and just have a think about m is the gradient. What is that c doing? So what does that c do when we're looking at y equals mx plus c? It gives you your y-intercept. Okay, so we've got the y-intercept. It is no different here because the y-intercept is where the x coordinate is 0. So if I've got y equals x cubed plus c, when x is 0, y is equal to c. And you can look here, those four curves are all x cubed. Okay, so they're all the x cubed curve, but they're just going through the y coordinate in a different place. So this green curve is x cubed plus 2. The red curve is x cubed. We've got x cubed plus 1, and that looks like x cubed plus 1.5. Okay, so we've got those curves going through different places. The point being that when I differentiate them, doesn't matter where it goes through on the y-axis, because I'm looking at the gradient function, and the gradient is the same. It just, as it changes, it's doing the same thing. So here we've got the same gradient, here we've got the same gradient. So as we change the x value, the gradient is remaining the same. So that's the first thing to kind of focus on. When you take a curve and you differentiate it, you are creating the gradient function. So then when I work it back and I do integration, it's giving me a whole range of curves that satisfy that gradient function. And that's what the plus c is doing. However, if we are given a point that lies on the curve, so that is the important bit here, that's supposed to be underlined, never mind, we can then find what c is. So if I tell you that the curve goes through 0, 0, then it has to be that curve. It has to be the red curve out of all the curves within that family. So here's the method. You integrate the function, you substitute the values from the coordinate that you're given, and then you solve your equation to find c. It shouldn't be that much different to using y equals mx plus c. It's the same sort of idea. So in the question, this is where notation is really important. You're recognising that you've got dy by dx. So we have the gradient function. So it's been differentiated. So in order to find the equation of the curve, we need to integrate it. So step 1 is integrate. So y is equal to the integral of x squared minus x plus 2 dx. Okay, so that's just integrating this function here. So dy by dx means we've differentiated it. Now, because I'm working backwards, I'm going back to y, because that's what we use when we're doing a curve, and I've got the integral sine dx. So what we get here is add 1 to the power, divide by it. Add 1 to the power, divide by it. Add 1 to the power, divide by it, plus c. Step 1. Okay. Once we have that, we're now going to use the coordinate 1, 2. So at 1, 2, because we know that that coordinate lies on the line, therefore when I substitute x equals 1 into here, the answer has to be 2. So we've got a third minus a half plus 2 plus c. So that's just substituting those values in to the equation that we've got in blue. So we've got 2 minus a third, if I take it to the other side, add a half minus 2. That takes me to c is equal to 1 over 6. Okay. Therefore, the equation of the curve that we are looking for is y is equal to x cubed over 3 minus x squared over 2 plus 2x plus 1/6. And that's it. So it's not really using anything new there. We're just doing integration and substitution. The key is understanding what each symbol is doing so that whatever you are presented with, you can move backwards and forwards between each of these categories.